You ever just stop and think about how quiet it seems out there? I
Yep.
mean, the universe is just so incredibly vast, right? Packed with stars.
Unimaginably so.
So, shouldn't it also be, well, teeming with someone else? That's the Fermi paradox, isn't it? Where is everybody?
It's the big question, definitely. And it nags at a lot of scientists and, well, probably a lot of us.
Yeah. So today we're diving into one really specific, kind of fascinating way scientists are tackling this, and it involves the Gaia missions data.
Exactly. We're not going super broad on SETI, the search for extraterrestrial intelligence or messaging extraterrestrial intelligence.
Those are huge fields on their own.
Huge. I mean, just to give you an idea, Jason Wright and colleagues did these reviews, SETI in 2020 and SETI in 2021.
Oh, yeah.
And they covered something like 75 papers in the first one, 98 in the second. So 173 papers combined just in those 2 years.
Wow. Okay. So, yeah, we're narrowing the focus today.
Way down. We're focusing very specifically on the hunt for Dyson spheres using data from Gaia, which is, I think, a really ingenious angle.
Okay. Dyson spheres. Sounds very sci-fi, but the concept itself is grounded in some, well, surprisingly logical ideas about advanced civilizations, right?
It is. And to really get why we'd look for them, we probably need to talk about the Kardashev scale first.
Ah, yes, Nikolai Kardashev, the Soviet astronomer.
That's the one. Back in 1964, he proposed this scale, basically ranking civilizations by how much energy they can use.
The idea being that more advanced means more power hungry.
Pretty much. As civilizations develop, their energy needs just keep escalating. It seems like a reasonable assumption.
So break down that scale for us. Like, what's a type I?
Okay, so a Type I civilization is one that can harness all the energy from its star that actually hits its home planet.
All the sunlight, starlight, everything reaching the planet.
Exactly. For Earth, that's roughly 2 times 10 to the 17 watts.
Okay. And how much do we use currently?
Our current global energy consumption is around 2 times 10 to the 13 watts.
So, wow, that's 10,000 times less. A type I is way beyond us.
A huge leap, yeah. That really puts it in perspective.
And then there's type 2. That sounds even bigger.
It is. A Type 2 civilization wouldn't just use the energy hitting its planet, it would harness the majority of the total energy output of its parent star.
The whole star's output, nearly all of it.
The vast majority,
Yeah.
yeah. Imagine capturing almost all the energy a star radiates in every direction.
That's staggering. And type 3?
Type 3 goes galactic. That's a civilization capable of tapping into the energy resources of its entire host galaxy.
Mind blown. Did Kardashev actually estimate when we might hit those levels? Seems pretty speculative.
Oh, it was definitely speculative, more of a thought experiment. But yeah, he did, assuming you had a 1% growth in energy use per year.
Which maybe sounds small, but compounds.
Exactly. He figured maybe 3,200 years to reach Type 2 and something like 5,800 years to hit Type 3.
Still a long way off, even with optimistic growth.
A very long way. But the key point for SETI, the search, is that any civilization wielding that kind of energy.
Might use some of it to communicate, to send signals across space.
Precisely. Having that much energy makes interstellar communication, or maybe other large-scale astroengineering projects, feasible. That energy has to go somewhere, do something.
And that brings us back to Dyson spheres as one possible outcome of needing all that type 2 energy.
Exactly. It's a potential, maybe even logical way a Type 2 civilization could actually gather that stellar energy.
Okay, so paint us a picture. What is a Dyson sphere? Is it like that solid shell you see in movies, encasing the star?
That's the popular image, definitely.
Uh-huh.
But when scientists talk about it, it's often more nuanced. It's a hypothetical megastructure, yes, built around a star
To capture its energy.
to capture a really significant fraction of its energy output. Think about it. A planet only intercepts a tiny, tiny sliver of its star's light.
Right, most of it just radiates out into empty space.
So if your energy needs are truly astronomical, going straight to the source makes sense. You build something to catch much more of it.
And this idea came from Freeman Dyson.
Yes, the physicist Freeman Dyson. He really popularized it in a key paper back in 1960. Search for artificial stellar sources of infrared radiation, it was called.
So he wasn't saying they must exist, but that they were a logical thing to look for.
Exactly. He argued they might be a natural consequence of a civilization's long-term survival and growing energy demands, a potentially detectable byproduct of advanced technology.
You mentioned it's not necessarily a solid shell, though. What else could it look like?
Well, yeah, the literature, like Jason Wright's review touches on this, suggests various forms. It could be a complete shell, maybe.
But that sounds incredibly difficult to build.
Immensely difficult, yeah.
Yeah.
More plausible might be Partial shells, or maybe a dense swarm of orbiting power collectors, sometimes called a Dyson swarm or net or rings.
Ah, okay,
Like-
like lots of individual collectors working together.
Right. The core idea is the same, intercepting a lot of starlight. The exact structure is less critical than the effect it would have.
Okay, so the effect. If one of these things is out there, light years away, how could we possibly detect it? We wouldn't see the structure itself.
No, almost certainly not directly. But we might see its side effects on the starlight.
How so?
The structure, whatever its form, would absorb the star's visible light, primarily. But thermodynamics tells us that energy doesn't just vanish, it has to be re-radiated.
As heat.
As heat, waste heat, essentially. And that waste heat would come out as infrared radiation.
So the star system would look normal in visible light, maybe dimmer, but unusually bright in infrared.
That's the key signature people first look for. A big, unexplained excess of infrared radiation. If a large chunk of the starlight is being absorbed and re-radiated as heat.
That could be a detectable sign, even across interstellar distances.
Potentially, yes.
Yeah.
Dyson himself pointed out that this waste heat might peak around 10 micrometers wavelength.
Which is in the mid-infrared range.
Exactly. So that made mid-infrared sky surveys the logical starting point for the search.
And have we done those searches? Did we find anything?
Oh, yes. The first big push came with IRS, the Infrared Astronomical Satellite, launched back in '83.
The first really sensitive all-sky look in the mid-infrared.
Right. Groundbreaking at the time. And several researchers, Schleich, Timofeev, Jugaku, and Ishimura, Kerrigan used IRS data and later data from other infrared missions.
To look for that excess heat signature.
They did. But unfortunately, none of those searches turned up any really slam dunk candidates. No confirmed Dyson spheres.
Lots of looking, no luck on the infrared front, at least not definitively. Were there other ideas, other ways to search?
Yes, people got creative. For instance, Luke Arnold suggested looking for transits.
Like how we find exoplanets when they pass in front of their star?
Kind of, yeah.
Yeah.
But instead of a tiny dip from a planet, you'd look for a much larger, maybe irregularly shaped dip caused by a huge megastructure passing in front of the star. Kepler data was proposed for that.
Interesting. Any others?
Teodorini suggested using the Spitzer Space Telescope for more sensitive infrared searches. Wright and colleagues used WISE data, the Wide Field Infrared Survey Explorer.
Still focused on infrared excess, mostly.
Mostly, yeah. Though Chen and Garrett took a totally different tack. They used the LOFAR radio telescope array to look for signatures of maybe even Type 3 civilizations, the galaxy-spanning ones.
Wow. And then, of course, there was that one star that got everyone talking for a while, Boyajian's star.
Ah, yes, Tabby's star. That caused quite a stir, didn't it? Around 2015.
The light curve was just so weird. Big, irregular dips in brightness.
Extremely weird.
Yeah.
And for a time, yes, an alien megastructure, maybe a partial Dyson swarm, was floated as one possible explanation. It fit some of the data surprisingly well initially.
But it didn't pan out.
No. Further studies, like those by Wright and Sigurdsson and others, strongly suggested more natural causes. The leading theory now involves clouds of dust from maybe disintegrating comets or something similar.
A natural explanation, not aliens. A classic SETI story, in a way.
It is. It really highlights how careful we have to be and how hard it is to rule out natural astrophysical phenomena. You need extraordinary evidence.
Okay, so that brings us back to Gaia. And this newer method, which isn't just about looking for extra heat, it's doing something different.
Totally different. Gaia's unique contribution here is its ability to help us find stars that appear underluminous.
Underluminous, meaning dimmer than expected.
Exactly. The logic is, if a Dyson sphere is blocking a big chunk of a star's light from reaching us, that star will look fainter than it should, given its distance and type.
Okay, but how do we know how bright it should look? That seems tricky.
That's where Gaia's incredible precision comes in. It measures stellar positions and therefore distances using trigonometric parallax with amazing accuracy.
Right, the apparent shift as Earth orbits the sun, a direct geometric distance.
The gold standard.
Yeah.
Now, we can also estimate a star's intrinsic brightness, and thus its distance, by looking at its spectrum, its light signature. This is called spectroscopic parallax.
So two different ways to estimate distance. One direct, trigonometric, one indirect, spectroscopic.
Precisely. And if those two methods give you significantly different answers for the same star,
If the direct parallax says it's close, but the spectrum makes it look like it should be much farther away to be that faint.
then maybe it is close. But something is blocking a lot of its light, making it appear fainter, and thus seem farther away spectroscopically.
Like a Dyson sphere intercepting the light.
That's the hypothesis.
Yeah.
This method, as Zackerson and Wright and others pointed out, also has a big advantage over just looking for infrared excess.
What's that?
It helps distinguish these potential candidates from distant things like active galactic nuclei, AGNs, which can sometimes masquerade as infrared bright sources in our own galaxy. Gaia's distance measurement anchors the star firmly within the Milky Way.
That's really clever, looking for the shadow, not just the glow. So when was this first actually tried with Gaia data?
The first application was by Zackerson and colleagues using Gaia's first data release, DR1.
Early days for Gaia.
Very early. They knew future releases would be even better, providing both distance estimates from the same dataset. But for this initial study, they combined Gaia DR1 parallax data from the TGAS part
TGS, right?
with spectroscopic distances from a ground-based survey called RV, specifically its fifth data release, RV-DR5.
Okay, so they mashed up Gaia's parallax with RV spectroscopy. How did they pick their targets?
They focused on stars that were in both catalogs, specifically main sequence stars similar to our sun types F, G, and K.
Why those types?
Because we understand their properties, the relationship between their spectra and luminosity pretty well, it makes the spectroscopic distance estimate more reliable.
Makes sense. So they compared the distances for these FGK stars.
For about 230,000 of them, yeah. Looking for statistically significant outliers where the Gaia parallax distance was much smaller, meaning much closer, than the RV spectroscopic distance implied.
And did they find any?
They did. After all the filtering and statistical checks, they ended up with 6 candidates showing this discrepancy.
6 out of 230,000. Pretty rare then.
Very rare. And the idea was these 6 could then be followed up with infrared telescopes like IRA's, WISE, Herschel, to see if they also showed excess heat, which would strengthen the case.
Did one of those 6 look particularly interesting?
Yes, one star, TYC 6111 111621, stood out as the most promising.
Okay. What were the numbers for that one?
The REVI data suggested a distance of around 222 parsecs, plus or minus a fair bit. But the Gaia DR1 parallax pointed to it being significantly closer.
And the interpretation was?
If the discrepancy was real and caused by a Dyson sphere, they calculated it would need to be a partial sphere covering about 77% of the star.
77%? That's huge.
It is. And it would dim the star's light by about 1.6 magnitudes in the optical and near-infrared, enough to explain why it looked fainter and thus spectroscopically farther away than its parallax suggested.
Wow. So for a moment there, it looked like maybe, just maybe?
There was definitely some excitement. It seemed like a potential first hit using this new method, but science moves fast sometimes.
Uh-oh. What happened?
While their paper was actually in review, Gaia's second data release, DR2, came out.
Better data.
Much better, more precise parallax for this star. And the DR2 parallax for TYC 611162-21 was, well, different, smaller, significantly smaller than the DR1 value.
Bringing the parallax distance and the spectroscopic distance closer together.
Much closer, essentially resolving the discrepancy. It strongly suggested the initial mismatch was likely due to the larger uncertainties in the earlier DR1 data, not a giant alien megastructure.
Ouch. So, excitement over.
Pretty much. They noted in the final paper. There was also the lingering possibility of an unseen binary companion messing with the star's position measurements, but the revised parallax was the main thing. Later Gaia data should clarify binaries anyway.
Okay, so that specific candidate faded, but the method itself, using Gaia to find underluminous stars by comparing distances, that's still valid, right?
Absolutely. That's the key takeaway. The study was a fantastic proof of concept. It showed the potential of this technique.
And future Gaia data releases will make it even more powerful.
Immensely so. Gaia DR3 and subsequent releases are a huge step up.
Yeah.
Vastly more stars, much higher precision astrometry, better identification of binary systems.
And crucially, getting both the trigonometric parallax and the spectroscopic data needed for the comparison from the single, consistent Gaia data set itself.
Exactly. That eliminates the potential issues of combining different surveys. It should allow us to spot these potential underluminous candidates with much higher confidence.
Sounds promising. Are there still challenges, though? Other things that could mimic that signature?
Oh, definitely. Nature is tricky. One potential confusion is something called gray dust.
Gray dust,
Yeah.
as opposed to regular dust.
Yeah. Most interstellar dust scatters blue light more than red, making stars behind it look redder. We call it reddening. But gray dust absorbs or scatters light more uniformly across wavelengths.
So it just makes the star look dimmer without changing its color much.
Exactly. And that dimming could potentially create the same kind of mismatch between parallax distance and spectroscopic distance that we're looking for with Dyson spheres.
Another natural explanation to rule out, always something.
Always something. So distinguishing true underluminosity due to obstruction from just, intervening gray dust is still a challenge we need to tackle.
Okay, so the Gaia search for Dyson sphere candidates is evolving, getting better, but it's just one piece of the much bigger SETI puzzle, isn't it?
Oh, absolutely. It's just one specific techno-signature search. As those reviews by Hawk Misra, Houston, and others show, there's a huge range of SETI activity.
Like what else, briefly?
Well, continuing searches for radio signals, looking for optical laser pulses, considering atmospheric pollution on exoplanets as a sign of industry.
Planetary pollution as a signal. Huh.
Yeah. And even more exotic ideas, like looking for evidence of star-lifting civilizations, manipulating their own star, maybe pulling material off it. Scoggins and colleagues explored how we might detect that.
Star lifting. Okay, the ideas get pretty wild.
The creativity in the field is amazing. People are really thinking outside the box about what advanced life might do and how we might see it.
It really underscores that we shouldn't just look for one thing. Not just radio, not just lasers, not just Dyson spheres.
Exactly. And as Wright and others emphasized recently, searching for both biosignatures, signs of life itself, and technosignatures is really important.
Why both?
Because finding one without the other tells you something interesting. Lots of life, but no tech. Maybe intelligence is rare or self-destructs. Lots of tech, but no simple life. That would be really bizarre. Seeing both helps us understand the whole picture of life's prevalence and longevity.
That makes sense. So wrapping this up then, we've explored this really specific kind of cutting-edge search for Dyson spheres using Gaia.
Focusing on that novel method of looking for underluminous stars by comparing distance measurements.
Right. And while that specific promising candidate, TYC 6111-111621, didn't quite hold up under scrutiny from later Gaia data.
The method itself is sound, and it's only getting more powerful as Gaia continues to deliver incredible data. This search is definitely ongoing.
So no confirmed Dyson sphere yet, but the tools and techniques are getting sharper.
Sharper all the time, it's a long game, this search. But the potential payoff, finding evidence of another technological civilization, it would be transformative.
It really makes you think, doesn't it? What would it mean if we finally found one? Conclusive evidence of a Type 2 civilization out there.
Or, perhaps just as profoundly, what does it mean if we keep looking with better and better tools and find nothing? Just the silence.
Back to the Fermi paradox again. Maybe that's a topic for another deep dive, what the non-detections might be telling us.
Could be. It's certainly food for thought. What does the continued silence imply about our own future or our uniqueness?
Definitely something to ponder.